The initial problem happened about 4:30 this morning. Radiation monitoring teams have been dispatched.
The history of nuclear energy is marked by a multitude of unfortunate events.
It was an accident at the 3 Mile Island nuclear power plant.
It was the first step in a nuclear nightmare.
We got too scared of nuclear in the 70s.
And just when it seemed there would be a nuclear energy renaissance, tragedy struck.
The images of destruction and flooding coming out of Japan are simply heartbreaking.
The nuclear crisis in Japan raises questions about nuclear safety here in the United States.
New York City sits 30 miles from a ticking time bomb, the Indian Point nuclear power plant.
But today, the advantages of going nuclear are being reconsidered.
There's a lot of untapped potential in what nuclear power can do for climate change and for our experience.
If I could just pick one thing, wave my magic wand, and we had it, I'd say nuclear everywhere, nuclear everything.
In this video, I'm going to take you inside Radiant, a company that's building small portable nuclear reactors.
We are focusing on making power accessible anywhere.
I sat down with the Radiant team to understand how they plan to do it. Is nuclear energy finally making a comeback? Let's find out. Doug Bernauer is the founder of Radiant, and he worked with Elon Musk directly while he was at SpaceX. To give me a bit of background on how Radiant got started, Doug walked me through his childhood and early career.
I grew up in Ohio, so I built model rockets as a kid and launched them in my own yard.
So then after high school, off to college?
Yes, and I thought I was going to do physics, and then changed my major about a year into it because I realized physics was going to be a lot of theorizing, and I really wanted to build things.
Doug joined SpaceX in 2007 before the company had successfully launched their first rocket. He was an avionics engineer at the time and has some great stories from the early days of SpaceX.
They were in El Segundo, they had a headquarters building, but they had 4 other buildings, and they were all scattered around, and there were just SpaceX people just walking the streets everywhere, and so much energy and excitement. It was really unbelievable. When we did get Falcon 1 Flight 4 to launch, I had my wife there with me, and then we watched it succeed. And then everybody rolled out these 2 little red wagons filled with champagne bottles and just distributed them, and everybody blasted just champagne everywhere. That was an awesome event.
After SpaceX started successfully launching Falcon rockets regularly, reusability became a major focus. Doug worked on the Grasshopper prototype that would eventually help the Falcon 9 land after returning to Earth. Delivery on Grasshopper allowed Doug to flex into a bunch of random Elon side projects. He worked on Hyperloop, and then started to think more about how exactly SpaceX was going to get back from Mars. After running the numbers on solar power as an option, Doug realized that nuclear power was far better.
The mission statement of SpaceX is making life multiplanetary. I started to strongly believe nuclear is really the only way to do that, and decided to leave and go found a company because it became really clear to me that it's actually the mission. So that's why Radiant is founded.
Doug understood that nuclear power had an incredible potential to make a difference here on Earth as well, so he started really focusing on building nuclear reactors. The first step in any new venture is building a team, so Doug called up his old colleague Bob.
I originally met Doug working on the Hyperloop prototype at SpaceX. Around 2019, Doug and I both left SpaceX. Around this same time that Doug and I started getting really into this, Project Pele was announced from the Department of Defense, which is build a portable micronuclear reactor for the DoD. That was really a clear sign that there's legitimate interest in this outside of just what we're trying to do. And from what we had seen from the other companies that were in the space, we were not confident that if we went to order one from somebody, we'd be able to get it in a time frame that was amenable to the goals we were trying to achieve.
The DoD would be a great customer here because they needed power in remote places, where electricity is much more expensive. So Radiant wouldn't need to compete with the grid-scale energy generation solutions that exist near major cities. Also, military bases are highly secure environments.
On the DoD application side, they're one of the world's largest carbon producers, right? So anything to offset their carbon production is a huge win.
The whole problem with nuclear is that there's no customer, there's nobody to push on the regulator, and there's no funds for development. But the DoD is all those things in one. So this is now, and this is a now or never thought that I got.
At this point, Doug and Bob had 2 key elements necessary to start a company: a great idea to solve a problem and a market that needed a solution. But they lacked one crucial element to bring their project to life: money. This is when Doug and Bob faced their company's first major challenge, convincing the Department of Defense to fund their project.
We submitted many times and got denied many times. It's very hard to break into the government grant process. You have to have an established track record, and it's, as a new company, you don't have an established track record until you have funding either from the government or from private entities. You can't get money from the government unless you've gotten money from the government, catch-22, or go to venture capital and make it happen. So that's what we started trying to do.
I got a $50,000 check from an angel investor, and it was the first one, and you never tell them in the first one. You know, $50,000 is nothing really to go on. I mean, I was paying myself a $0 salary and just watching my bank account go like this, and I'm fine with it. But you know, later on I figured out when I want to do a Series A, and that's March 2022 we did it.
Part of our ethos as a company is to be anti-stealth, and so what that means is that we have open doors, that anyone who wants to come pop by and see us building a nuclear reactor can come by and see us building a nuclear reactor. And that actually was a very effective raise strategy, because anytime an investor was like, hey, what are you guys up to? Can I come see? Can you show me slides? And we were always like, hey, instead of slides, come see us. And the best way to sell what we're doing is to be here and can see us building it, and you can meet the team and meet the energy.
To understand how Radiant plans to build small nuclear reactors, it's essential to grasp a few key concepts. Today, nuclear reactors generate energy through a process known as nuclear fission. Fission is a reaction achieved by bombarding neutrons into an atom of a chemical element such as uranium.
The uranium nucleus will first take a neutron in, it will become unstable and will rip itself apart. And that fission releases energy as well as other neutrons and gammas.
In a conventional reactor, the heat energy produced by nuclear fission is used to generate steam, which drives turbines to produce electricity.
The amount of power you generate is basically set by the number of neutrons you have in flight in the reactor system at a time. So to control the amount of power, you control the amount of neutrons, and you do that by raising and lowering boron into the core, because when a neutron collides with boron, it's captured and just stays. So we call that a neutron poison. For us, we have blades of boron around the outside of the system. So basically like wipers that are sitting in front of a chunk of graphite. So the graphite acts as a reflector, so the neutron comes in, hits it, bounces back into the core. When we don't want that neutron to be able to bounce back into the core, we slide a sheet of boron in front of it. But this is the blade actuator for the reactor system. These here are tubes that are filled with boron carbide, which is a neutron poison material. The neutrons that are coming from inside of the reactor core come into here and get absorbed by the boron that's inside these tubes. Putting the tubes in the way of the neutrons slows down the nuclear reaction, and it's how we turn off the core. Rotating these outwards and exposing the material that's behind them, which is graphite, we can reflect neutrons off that graphite back into the reactor core and then increase the rate of reactivity, the number of neutrons that are in the core, and thus the amount of power that's produced by the core. What we're going to do is simulate a cybersecurity incident where someone has overridden the control of the motors and we are no longer able to directly control them. But the safety controller detects that the reactor power is outside of bounds and we're no longer in control of the system and forces it to shut down. Go for it. So what he's done is told it to command the actuators outside of their control bounds, and then the safety system forces it into the closed position.
Before you can actually go and build anything this ambitious, you need to understand exactly how the system works in simulation. So the Radiant team started writing software to act as a digital twin of the full-scale reactor they would eventually build. A big part of what made SpaceX work was their focus on tight iteration cycles. The company failed often, rockets exploded, but failure was always quick and every setback taught them an important lesson. Doug took this philosophy of quick iteration to Radiant.
I just ran as many designs as I could. And then I'd get the numbers and I'd look at them and I'd go, well, this reactor lasts this long, this one lasts this long, but it costs this much more. The more I did it, the more certain I became that it was really possible to do this, to design a portable microreactor that was economically viable.
The Radiant team realized that many of the concepts applied in the design of conventional nuclear reactors wouldn't work for smaller ones, so they decided to look for inspiration elsewhere.
We started from looking at space reactors because a normal reactor has the core and it has control rods, and when you insert those rods, the reactor's fully shut down if all the rods are in. And then if you start to raise those rods, at some point it goes critical. We didn't want to make a reactor with control rods because we wanted to ship an upright reactor, which would make it less challenging for transportation. And if you have to make it so you have control rods, that's about double the height of the pressure vessel. You would have something that would go outside of the shipping container size box, and so it would just be bad. Yet if you make a reactor small enough, instead of putting rods into it, you can have control blades inside of it that just rotate towards the core and control it in the same way. And that had been done before in space reactors.
There were still several key pieces of technology that Radiant had to develop in-house. For example, the system they used to cool the reactor.
So our helium circulator is a purpose-built motor that's meant to operate at the temperatures that the nuclear reactor runs at and the pressure that the nuclear reactor runs at.
In order to make power, you really don't want to use the helium that you're cycling through a reactor in your power loop because it could entrain little particles of the steel or of the graphite that could become radioactive. So you actually use a heat exchanger, which keeps the helium all on this side, keeps your other fluid on that side, and once you do it, you get that isolation from the nuclear stuff. Safety is on that side of this heat exchanger. It's this super important component.
It's essentially putting together a ground fluid plumbing system. A lot of the test systems that I worked on at SpaceX were a lot of fluid systems, a lot of piping systems, a lot of ground support equipment to be able to provide the fluids to the vehicles that we were testing for structural testing. So use that experience to put together the piping system.
Another crucial component that the Radiant team had to develop on their own was the structure that supports the reactor vessel.
There's a lot of difficulty in supporting the reactor because it's increasing with temperature, so it's expanding out, and so you have high temperature conditions at the strut locations and changing size.
The Radiant team also had to innovate in the design of the reactor core.
The core design iteration it used to just be all graphite with like fuel rods and then like helium. Fuel rod, helium, like that.
Okay.
We have totally changed the design.
Yeah.
That design, if you dropped it into water and it flooded, it would go critical.
Sure.
This won't.
Okay. The new one.
This new design,
Yeah.
which has these large holes.
Sure.
And so the helium actually flows around the outside of a material that goes in there.
Yep.
And these are all fuel.
Okay.
All these locations.
It's a common misconception that nuclear reactors are dangerous. In fact, when you look at the data for deaths per terawatt hour of energy production, nuclear is safer than windmills. And this data includes Chernobyl, which happened 38 years ago.
People picture waste in particular as a much more dangerous item than it is. I think it's well handled in the United States.
Other big misconceptions, a lot of people just generally think that like being near nuclear plants is scary, whether that's direct radiation or they see like the big steam towers and they assume something bad's coming out of it and it's not just water vapor.
It's kind of those misconceptions that we try to address and make sure that people are educated about what nuclear technology actually is. We know that we have to change some hearts and minds around nuclear and show people that nuclear is safe, it's reliable, it's clean.
The beauty of Radiant's design is that it's even safer than traditional light water reactors.
The first critical differentiator is what is your working fluid for cooling the system, which ours is helium. So that categorizes us rather than as a water reactor as a high temperature gas reactor. Helium is a popular choice for high temperature gas reactors because it doesn't interact with the neutron radiation inside the core. So it can't, the term for that is activate, it can't become radioactive.
And the small portable design unlocks a bunch of unique capabilities.
We are focusing on replacing diesel generators and making power accessible anywhere. And that's done through nuclear technology. So these microreactors are transportable by air, land, and sea. They fit in the back of a C-17 aircraft, can be delivered on site quickly and up and operational within a couple days. So it's really the power that nuclear people want.
These can be brought into emergency situations to provide clean, reliable power on short notice. They can even be deployed along highways where grid power is unreliable to help charge electric vehicles. And for military bases, it can often be a challenge to continually resupply diesel generators with fuel. Once these are installed, they're good to go for years. The team is aiming to build a compact nuclear reactor with all the equipment necessary to generate electricity in a mass-producible and easily transportable package. They call it Kaleidos. It'll be able to provide over 110 times the energy density of existing diesel systems. While generating electricity, Kaleidos can also provide 1.9 megawatts of thermal power for facility heating or water desalination.
Kaleidos is a dual-use reactor. It is meant to have commercial customers and military customers, not just to be a military product. Kaleidos is in pre-application, and we're planning the budget and resources to be able to do our reviews on time to get to delivering products starting in 2028.
The Radiant team takes security extremely seriously.
All the work I was doing off of the beginning was, how do I figure out how to make something that's safe? How do we know that we're not going to be capable of melting the fuel? And this is nuclear reactor analysis.
Kaleidos runs on a type of nuclear material called trisoparticles. A single particle is about the size of a poppy seed and is made by combining uranium, oxygen, and carbon. Each particle is covered by ceramic and carbon materials before being formed into larger cylinders for use in reactors.
This is one of the graphite monoliths that make up the reactor core. These tubes get installed inside the reactor core, and then stacked up inside of there are these different graphite pieces that make up the actual fuel positions. Trisoparticles get press formed into small cylinders of graphite, and then those get dropped into these positions and stacked up. There will be several of these positions all the way around in the production system, and then those get installed into these monoliths, and then those monoliths are tiled around the reactor core to make up the full reactor system.
Still, it's important to make sure that nuclear material is kept under lock and key at all times. There are tons of regulations in place to make sure nuclear material is handled appropriately. To ensure Kaleidos is safe, the Radiant team is currently conducting various tests.
This test rig behind me is our passive cool down test. What we're doing is we're building a full reactor worth of components. And the point of running this test is to simulate an accident scenario of the full reactor system. After you've shut down the reactor in response to an emergency, if you don't have helium that you're forcing through the reactor still, it will continue to produce heat for some amount of time afterward. This is called decay heat. And we want to be able to demonstrate with this system that we have the ability to keep it passively cool in the scenario where we have shut it down in an emergency.
Because of the size of our reactor being so small, we're able to passively cool the reactor. What does that mean? It means that we can bring the reactor back to safe temperatures without actively cooling the system. So you can see we have the core and our steel pressure vessel. Going around that will be what we call our air jacket. The air jacket is actually an absence of stuff. And so when the SCRAM system is triggered, the air jacket will open. Natural convection will rush by this big, beautiful hunk of steel that you see, and that will be what is able to return the reactor to safe temperatures. This is what we call our pressure vessel. Inside is where our core sits. So for those who aren't familiar with nuclear, that's where the reaction actually happens. In this, we'll put 37 graphite monoliths. Following from there, we'll push cold helium into the reactor that will flow up down through the graphite core, and then we'll have hot helium that we pull out of the reactor. This is our helium loop here, now connected to the prototype of the reactor core. And what's happening here is this is where we both push in cold helium and extract hot helium from the core for it then to go to our secondary loop. Our secondary loop where we'll generate power is still under development.
Kaleidos will also have multiple benefits for the environment.
There's a lot of untapped potential in what nuclear power can do for climate change and for our experience.
Where a microreactor Radiant operates, there's no spent fuel stored on site. It doesn't leave a permanent or lasting change to the environment around it. That means that you could put a playground there, you can build a school there. No radiation, no emissions, no environmental change. And then once you're kind of done with the unit, it comes back to our facility.
It's not enough for these reactors to just be better for the environment. In order to really take off, they have to be cheaper than the alternatives. That's the story we've seen play out with electric vehicles, and decisions about power generation in remote locations are even more economically driven. The market for diesel generators is huge too. Just in the United States, it's over $5 billion. Radiant reactors have the advantage of not needing to refuel for years, so if they can build and deploy these at a competitive price, they'll see massive adoption. The government is starting to support nuclear power more and more. The Office of Nuclear Energy has the Advanced Reactor Demonstration Program, which provides funding for projects like this. The key metric that Doug and the Radiant team are working against is the price of diesel fuel. Now, small reactors do come with trade-offs. You would need hundreds or thousands of them to power an entire city, but the opportunity to replace 1 megawatt diesel reactors is so big that it doesn't really matter. Large reactors are well understood machines, but going smaller is just plain safer. There are dozens of small nuclear reactors on college campuses around the country that no one ever really thinks about. They're used for nuclear research and do contain radioactive material, but it's such a small amount, it's just a low-stakes operation. And it's my personal hope that once these microreactors are being produced en masse, people will just be a lot less scared of nuclear in general, and we'll see more reactors get built at all sizes. Mass manufacturing is truly magical. Once an industry is producing thousands or millions of something, the quality skyrockets and the price plummets. This has been true for computers, phones, and even rockets. A big part of the problem with nuclear power is that we just don't build that many of these plants. For example, the construction of the Vogtle 3 and Vogtle 4 nuclear plants saw delays of over 7 years and cost overruns of over $15 billion, doubling the original budget. That makes it hard for investors to justify new projects, but Radiant is aiming to change that. If you're building a new reactor, you can't exactly test it in your backyard, so Doug and the Radiant team established a relationship with the Idaho National Laboratory.
The Idaho National Lab historically has been where all of the nuclear testing has happened in the United States.
The goal is to test our prototype reactor, so that's just the core and primary loop, in what's called the dome facilities.
Essentially, the Idaho National Lab is acting as the design authority for the test reactor that we want to build, so they're a part of our design reviews as we develop the reactor system.
This would allow them to take advantage of the research and expertise that already existed in the industry, as well as eventually go and test their new design.
We've started some good work with Idaho National Laboratory to do fuel irradiation, which is pretty critical to our commercialization story. We delivered a conceptual design to Idaho National Laboratory. So the next big one is our preliminary documented safety analysis, and that's later this fall. On January 1st, 2026, we're gonna have a reactor at Idaho National Laboratory so we can do a host of startup physics tests all before we start to go up to power.
We're going to do the first fueled reactor test in 50 years.
We like to use that as a line in the sand for comparing Radiant against the rest of the market. And so being kind of first to show that you can meet your technical milestones gives confidence for the commercial market and the potential customers that we're talking to.
Radiant is still a young company with a bunch of huge challenges in front of them.
The biggest one for the company is the PCT, the passive cooldown test, later this summer. Hopefully everything matches like the models that we had predicted of that. And then after that, it's build our license applications for the NRC. That way we can start selling the unit commercially.
If we're successful in 2026, there's a factory site waiting in a friendly Western state.
We're part of the first group of folks trying to build a microreactor and commercialize it, and so the industry has just not been tested in this way yet. A lot of our team is solving problems for the first time that just we haven't had to do before, and we don't have a one-to-one model for how to do that, but we've got a lot of creative thinkers and problem solvers who are making progress with the agencies and folks we need to do. Doug is the inventor and visionary. He's always 5 to 10 to 15 years out in his thinking and helps us see that future. And Bob and Tori both help us make that future a reality. Bob and Doug and Tori genuinely care about making sure that our people here have a good experience and that they feel like they are a part of this dream and mission that they created.
I hope you enjoyed learning about this company. Stay tuned for the next one.